calculate basically the same things that last week. So wall skin friction coefficient for different Reynolds theta. So at different x coordinates, we'll have a different theta. That is the displacement thickness of the boundary layer, we define here. So we'll have also different Reynolds theta along the plate. We also have different wall shear stresses. Different wall shear stresses means different skin friction coefficient. So you calculate the skin friction coefficient as a function of the wall shear stress. In order to calculate these values, we can create some lines where we are plotting our results, or we are saving text files with the variables that we are interested in. So the lines that I will create are shown there. And I'll go from domain on the top here. You can find domain, also surface, create. This is another way to create lines or surfaces where you want to plot your variables. And there I select the line, rake. Yes?
Oh, create. We go to create.
Yeah, the domain, surface, create. And there is this option. So,
And then line.
if you go from there, you will find this window where you can set the surface name. So I'll set it to center line for the first one. Type is aligned. And then I need to set the endpoints that are shown also there on the whiteboard. So the first endpoint is 0 minus 0.5 because the y is, so we are taking the value at this y. So that is in the middle of the domain, our geometry. x0 means the beginning of the plate. And then the first point, since we want to create this line along the plate, this has also a z equal to 0. Instead, the second endpoint is at x that is equal to, in this case I put it to 2. I think the plate is long 0.2 from the front, so I was just setting a much larger value, it doesn't matter. So I'm covering the whole domain. The same y minus 0.5 and the same z 0. And I can hit create. When you do that, you see that the name of the surface of the line is changing. That means that you have created that line and now you are ready to create a new one. So now you can create the next ones that are shown there. So the lines perpendicular to the plate, that means this kind of lines at different axes. And the axes are shown here. So we have selected those in order to get like a distribution for those quantities along the plate. So I'll call the first line x01. So for an x equal to 0.1. So the first value of the endpoint is you can see x. So I'm going to set 0.1. Y is minus 0.5, so always in the middle of the domain. The first z is 0, so we are starting from the plate. Then the second x is once again 0.1. The second y is the same, like minus 0.5. And now we select z in a way that we can cover the whole boundary layer, and 0.1 is large enough. So we select that. and we can hit create. We do the same for every line shown there. So for example, then here instead of line 8, I'll write line x02, and I'm changing just the x value. So instead of 0.1, here I set 0.2 for both endpoints. And I don't touch the other coordinates. Then I do the same for x04. So 0.4, 0.4. Then we have x06. So 0.6. Then we have x1. So I'm going to call it x10. 1 and 1. Create, and then the last one is line at x equal to 1.5, so 15 here and here 1.5. And create. So I can close now this window, and if I want to check that I'm creating the correct lines, I can go in general, in the setup general, where I have this display, and I deselect all of the surfaces using this X button on the right, and then I can select the lines that I created. So center line, and then all the lines perpendicular to the plate, so I can display. I can also select the plate so that I'm showing the plate also in this chart, in this the display, and so that looks fine. That looks correct. You should have something like this, like lines you plotted. Yes.
Select all of these and then
You can select all of them, and if you want to check the
I think it's easier than some. Because last week I took
it's more like
yeah, that's all. And then also the plate, if you want to check where the plate is, and then display.
So when we select the plate, we will see
The surface.
the surface.
Yeah.
Yeah, excellent.
So now we can plot variables along these lines, or also write some text files that we can use in for post-processing, like in Excel, like we did last week. We'll do also this week. So we can close this display, and now we can go in results. There is this plots. I double click on plots, and here you can select this XY plot. So you double click on either on here or on the left here to XY plot. So with this, in this window you can plot your variables or you can save them. I typically deselect these node values. That means I'm not getting the values at the nodes, but I prefer to get also some kind of interpolation between the nodes. So I'm not exactly sure how Fluent is choosing which are the points, but typically that works better for me to get like better visualization of the results, especially close to the wall, because there you have depending on the grid, like you can show like a better distribution for the boundary layer. So then we can start with the center line. So the center line, we can leave this position on x-axis, since the center line is along the x-axis. So plot direction x, that's correct. And in y-axis function, we can plot the wall shear stress, because we need the wall shear stress along the plane. So we go to wall fluxes here, and the option is already there, so it's wall shear stress. In surfaces, we select center line, and we can plot. We can also select order points here. Doesn't change it much for the plot, but it will change when we write the file, because it's ordering for increasing the x value. So you should get something like this kind of distribution. So very high at x equal to 0, and then it goes down, the wall shear stress. And we can save now the file. So we select this write to file option. So instead of save plot, now we have write. So we hit that, and we can save the. Now we have the our working folder. We can save a file. I'll call it tau_w. That stands for tau wall, so wall shear stress. And I also had .xy extension, so it's my Windows will automatically understand this XY text file, and okay. So I saved the tau wall x file in the working folder. Then we can do the same for the lines perpendicular to the plate. Now let's first plot. So I will deselect the write to file. These are, well, basically you can choose the x-axis also from either deselecting this option and selecting then the x-axis on the right, or you can change the plot direction. You know that these lines are in the direction perpendicular to the plate, that we call y, like our y class, but in the geometry. Okay, so if I'm showing this, you can see that these lines over here in Fluent are in the z direction. So we need to set our plot direction to x0, y0, z1. So that means that you want to plot the variables along the z-axis. And you can select, in this case, we have basically constant density, 1.17. We have constant viscosity, so the only distribution that we need is the velocity. So in y-axis function, we select velocity, and we want to show the velocity magnitude. Then we select the right lines, so not the center line, because there we have no strip wall condition. That means the velocity is 0, so it's the same velocity of the solid. But we want to plot the velocity at line x1, x02, 04, 06, 10, and 15. So we select the lines perpendicular to the plate, and we can plot them to see that they look well. I don't know why now I have scattered points. Last week I had some continuous, like solid line, and no idea why it's different, but still the results look fine, so that it's okay. So you should have this kind of distribution for different axes, so different locations along the plane. Next, you can save these values. This is like for direction means that yeah, this is like on the axis. And you can select the write to file option once you have these charts, so that means they are correct. And we can write this either all together. Now I was thinking that maybe it's better to do separate files, so it's easier to copy in the Excel. So I'll select just lines x01. I can write. So this is going to be u01. So the velocity at x equal to 0,1 dot xy. And then I can do the same for all the other lines. So I deselect line 01, select 02, and save the file. Zero 04 also. Zero 06. Then 1, call it 10, and 15. So now you have text files with your velocity distributions at different locations along the plane. Before leaving Fluent, we can check in the exercise that we should plot the additive viscosity at different locations. So x equals 0.2, 0.4, and 0.6. So we can do that here in this window. So we can, instead of write to file, so we deselect write to file, since we want only to plot this. Z direction is correct. In the y-axis function, we need to find the additive viscosity. So we go, instead of velocity, we select turbulence. And in turbulence, here you can find in the second box, there is modified turbulent viscosity. This is the variable that Fluent is calculating for the Spalart-Talmaras, so that nu tilde. That's not what we want. We want the additive viscosity, that is the turbulent viscosity, so the second variable. And we select the lines perpendicular to the plate where we want to plot that. And we can plot. In this case, we needed just 02, 04, and 06. So like this. So this is the distribution of the additive viscosity. So it gets larger as we move along the plate.
No.
So larger and wider.
That's 2.5, right? Oh, yeah, that's good.
Okay. Now we can move in Excel. So we can close this.
Sorry, for the viscosity for all lines or for outside different lines at the track?
It was only for lines 02, 04, and 06.
Oh. So other lines?
No. It's just the distribution. You can just select the right to file and click on plot line. So let's open Excel. I'll save this. So in our working folder now we have these files. So for the wall shear stress and all the velocity distributions, so we'll open all of them. These are text files. So if
Yes. So we call this line and then
Okay.
Where you said.
Then you can see
Yeah,
each of them, like for each one.
No.
Okay.
Oh, I
So
see.
there are some photos where you have your
So for that wall, that's
Because it's like something like this.
maybe next step we plot
Just copy it.
Okay, yeah, you can copy.
so the next time.
Let me try opening it. Just a second.
You are the viscosity. So then you can select this is modified. You select the turbulent viscosity. At x0. Zero
Try it.
and you can plot this. So this is you can attach this screenshot homework like this kind of one of the requests.
You need to tell which data. Tell like choose right here and then tell into my folder.
No, you can use the screenshot. So then we can so open these files,
Yeah, we don't.
text files, and we can copy
Open it one by one, I guess.
all of them. So we start from the tau wall, the wall shear stress.
Do something like this.
So Control A, Control C, and Control V.
Yes.
for that wall, direction was X or Z to.
It's the x-axis. So this is along the center line that is kind of the line over here. So that's
Okay.
along the plane. And then we can copy all of the other plots. So that was for tau wall, close this one. Then I'll go to x equal to 0, 1, Control A, Control C, Control V. And also for the other files. 2, 4, 6, 10, and 15. Once you have all of these columns, distributions, basically the first column is the Z or the Y, so the coordinates, so the distance from the wall, basically. And you can see for that, except for the wall shear stress that is calculated at along the x-axis, all the others share the same values for the distance from the wall. So we don't need, let's say, the first column. We can just keep the first one for the first distribution at x equals 0.1. So what I'll do, I'll select all of these columns, keeping control, and then I'll right click and delete these columns. So I'll also delete these rows. And now I can write what these are. So this is X, this is tau wall, this is, let's call it now Y, and this is U at x01, this is U at 02, U at 0.4, this is U at 0.6, U at 1, and U at 1.5. Then I can also delete these empty rows, these empty columns. So I get just this kind of distribution over here. The x versus tau volt, y versus the velocity distribution at different axes values. So then the next thing we can do is to so what we need here is to calculate, let's see, the Reynolds theta. For Reynolds theta, we need theta. There, theta is this integral. So that basically is the sum of the delta theta along the line perpendicular to the plate. So the delta theta is u as a function of y over u infinite. U infinite is the free stream velocity times 1 minus u y over u infinite times delta y, that is the cell size, or the distance, let's say, between the 2 points along the line. So first of all, we can calculate the u infinite. So let's make here x equals 0.1, 0.2, 0.4, let's see, 1 and 1.5. So that now we can calculate different variables at different locations. The first one is u infinite, which is the free stream velocity. And we calculate the free stream velocity as the maximum value, so max function in Excel, open round bracket, and I select the column related to x equal to 0.1 for the velocity. So I go from here to the bottom, so Control Shift down, and I select this column over here, and I get this value. So this is the maximum value of that column, which corresponds to my free stream velocity in x equals 0.1. I can just pull this value for different axes. So I calculate it for different values of x. Now that you know u infinite, we can calculate the delta theta. So I'll copy this, or no. Copy this here, but instead of x, this is the theta at x equals 0.1, and then at 0.2, 0.4, 0.6, 1, and 1.5. And so here I set the formula to calculate delta theta has, so we have initially the ratio between uy over u infinite. So uy is, let's try to show it, what I'm going to do. So if this is our line, this is the wall. What we are doing, we are getting the values of several velocity distribution along this line. So I calculate the velocity. So this is, for example, u0, this is u1. The value between u0 and u1 for me is going to be the arithmetic average. So I'm just calculating it as u0 plus u1 over 2. So for each cell, for each section, I calculate the arithmetic average of the velocity as uy. So this is going to be equal to, open round bracket, the velocity of the first point plus the velocity in the second point at x equals 0.1 divided by 2. So this is the arithmetic average of velocity between those 2 points over u infinite, that is here, for x equal to 0.1. Then we need to multiply this times 1 minus the same ratio, u over u infinite. So we can just copy the first part of the formula, that is the average velocity over u infinite. So Control C, Control V, and close round bracket, times delta y, there is simply the second y value minus, sorry, I'll put a round bracket here. So the first values of y minus, sorry, the second value of y minus the first values of y. So this is the delta y for that, between those 2 points. And enter. So there I get the value of the delta theta, so the momentum thickness for that between those 2 points. If you want to pull this formula at different axes and along also different y, we need to lock some cells. So we can lock u infinite in the y direction. So we lock the number, we put a dollar between 4 here, and also in the second u infinite, we lock the 4. Instead, we need to lock also the delta y, and we need to lock in this case the letter. So in the horizontal direction, we lock with the dollar dd. So that we can pull it in vertical direction, but we cannot pull it in the horizontal direction. And we can pull this then to the right side. Let's check if we have done things correctly. I select the values for x equal to 0.4, and that's correct. So it's getting the right values for the velocity, for the y, and for the twisting velocity. And then I select all of them and pull them also in the vertical direction up to the before last value. So I can calculate this until the last value.
Because the first one is the same. This is the same. The first one.
So I get delta theta distribution. So the delta theta values for each section that I'm dividing my line perpendicular to the plate.
Sorry, can you just again repeat it? At u infinite, at which position you selected u infinite? Right.
U infinite is the maximum value of this column. So for example, for u infinite at x equals 0.1 is the maximum value of the velocity distribution at 0.1.
Why not choose 0.2? The same.
The 0.2 then is going to be the u infinite at 0.2.
Okay.
So we select like the maximum value should be, let's say, the value of the velocity.
Basically, this is your y.
So if this is our line, basically what we have is something like this, our boundary layer.
You can just like fill it.
So at the top you are in the twisting region. So this is going to be, and this is going to be different between, well, not much different. The Mach number is still constant, 0.2, but
One is longer than
advanced.
the velocity on the, yeah, okay.
Here I'm setting like a decimal separator of the point, so that when I copy paste those values are kind of, Excel is reading the correct value for. Otherwise you may get some different kind of values. I don't know how it's set and by default how that works, but you should change that option if you see that you have some strange things happening. Okay, let's move on. So now that we have delta theta, we can calculate the theta. So this is the sum just of all the delta theta. So I select this column. For each x, I calculate theta as the sum of the respective column. And then once I have this, let's also write here the rho infinite value. This is a constant for each line, but let's still write 1.17. And we can pull it even though this is constant. And then also mu infinite, so the dynamic viscosity. This is also constant and is equal to 1.7894. 10 to the power of minus 5. And I can put this also on the horizontal direction for different axes. Now that we have these values, we can calculate the Reynolds theta at each x value. So this is going to be equal to, so we follow the formula there on the whiteboard. It's rho infinite times u infinite times theta over mu infinite. So we get the values of Reynolds theta for this x. We can just pull it horizontally and we get the values of Reynolds theta for all the other x locations. Okay, then next thing is we need to, if we go in the exercise page, we need to plot the Wolfskin friction coefficient for different Reynolds theta. So we need to calculate CF. CF, we need rho infinite, we have them, and the wall shear stress. So we need to calculate tau wall at different x locations. So we need to get the correct value here, and we need to find it in the column of tau wall. So let's get a better view of this. I will decrease the decimal here for these columns. So the first tau wall is for x equal to 0.1. So I find in the first column x equal to 0.1, or the closest value to that, and I select the value in the second column. That is the tau wall at x equal to 0.1. And I do the same also for x equal to 0.2. So I go first column 0.2 and select the value relative to that. And so on also for the other values of x. So 0.4, 0.6, this is 1, and 1.5. So these are the values of the wall shear stress at different x locations, extracted from the columns here describing the tau wall distributions along the x-axis. Once we have that, we can calculate the screen friction coefficient, CF. So CF is equal to the ratio between, like it's given there, the ratio between tau wall over the product between 0.5 times rho infinite times u infinite and we can just pull this on the horizontal direction. You can check, then you can check these values with the one in the website. Here you see that you have distribution for CF. You also have links to get the data points at different Reynolds theta for the correct CF. So we can compare the results we got at different axes, and so different Reynolds theta with these charts.
That you measure effectively.
Maybe I've done some of this.
And use u infinite square.
Yes. So it's L for the power root.
Basically, it's compression on the
The velocity UV at the power root. Okay, now we have that. The next thing we are asked is to calculate the law of the wall at Reynolds theta equal to 10,000. So we get, here we have the values of Reynolds theta. You can see that 10,000 is, so 10 to the power of 4, it's x equal to 1.5. For the mixing length model, we get that at x equal to 0.6, so it's already a different solution. You can check, you can see from that. So we need to plot the law of the wall at Reynolds theta 10,000, so at x equal to 1.5. In order to do that, we need to calculate the u tau, the friction velocity. So the law of the wall means plotting y plus and u plus. For these values, we need the u tau to calculate y plus and u plus. And u tau is given here, is the square root between the ratio between the wall shear stress and the density. So u tau, we can calculate it for all of the x coordinates. So it's the square root, so I use the function sqrt of the ratio between tau wall and rho wall. Rho wall is, well, the density is constant, so we can use the infinite value. So the value at extreme condition. And okay. So this is the u tau for x equal to 0.1. You can just put it for all the cells. And so since we need to plot the y plus and u plus at Reynolds theta equal to 10,000, so x equal to 1.5, so we use these values of u tau, 2.49.
difference between y.
Now we need to create charts, or we need to calculate the value of
U naught plus V1.
u plus and y plus. So we do that here. So let's call this first column is y, second column is y plus,
So like an average.
or yes, and then u plus. This is done for x equal to 1.5. So y, distance from the wall, we can just copy, select the value of the y that we have for the lines perpendicular to the plate.
Difference between it.
Y plus is, we use the formula to calculate y plus, so E is equal to y times u tau, friction velocity. So we select u tau at x equal to 1.5 over nu wall. Nu wall is the kinematic viscosity. So the kinematic viscosity is given here. Is the ratio between dynamic viscosity that we have is the wall value is constant, so it's the same like the infinite value, and rho. So we divide by the ratio between mu infinite over rho infinite, which is the kinematic viscosity, nu wall. Okay, and then finally we can calculate u plus. That is simply the ratio between the velocity at 1.5 at x over 1.5. So we select this value of the velocity distribution here over u tau. So the value of u tau at x equal 1.5. And okay. Now, if you want to pull this along the different y values, we need to log some cells. So for the y plus, we need to log the, let's see, the, not the y value, we need to log the u tau value, so $2 at both letter and number, and then also the mu infinite rho infinite values, so dollars here. I do the same for u plus. So u plus, I will not log j2, that is the value of the velocity, because this is changing along the line, but I log the u tau, so q25. And then I can just pull this up to the last value of y and u, and here you get your y plus u plus distribution. We're running out of time, but it's the last point of the exercise. So it's plotting this. So let's create a chart. So insert chart. I select the data. So the x values for our plot is going to be the y plus, and the y value is going to be the u plus. Okay. And here it doesn't make much sense. I mean, because as you know, on the x location, the y plus, this should be a logarithmic axis. If you double click here, you select logarithm scale, then here you get your law of the wall. So you can see the different layer, viscous sublayer, log layer, and I'm missing the name of the last layer, the defect layer. And so you can compare also this distribution with the theory values. We also have in the website this kind of distribution here. You can find the text file at Renault theta equal to 10,000 for y plus and u plus. So you can compare CFD values with this theoretical or.
When do you get a raw wall?
Rho wall is rho infinite, like it's constant everywhere. We are assuming a constant density. And additionally, you can also compare the results with the mixing length model. So you can check which one is more accurate. Of course, the answer will be that the Spalart-Ammar is more accurate, since we are solving one transport equation to calculate the turbulence in the flow. Okay, thank you. If you have any questions.